Hello. So, let us continue with the next class. Just to briefly recapitulate, last class we have studied the base classifier in detail. We have derived the base classifier for the general loss function, and we have also proved the optimality of the general base classifier. Optimality in the sense that no other classifier can achieve lower risk than base classifier. So, for risk minimization, we showed that the base classifier is the optimal classifier, and we have also seen several special cases of what the classifier looks like. For example, for 0-1 loss function, how it looks like, and also for special classes of class conditional density such as normal and so on, we have analytically derived the base classifier. So, we have seen some examples of how one derives base classifier. So, this class will start with another simple example of deriving base classifier in a slightly different setting. Then we will look at base error, how to calculate the error of base classifier, and then we will move on to a few other criteria for classification. Okay. So, let us start with an example. Let us say we have k classes, and as I said when we did the base classifier last class, that the actions of the classifier need not necessarily have to be class labels. They can be more than the class labels. So, let us take an example where the classifier is allowed the option to reject a pattern. As you look at the pattern and say, no, I cannot classify. And let us assume that this is done by the classifier assigning a class k plus 1 to the pattern. So, that is k classes. So, class label takes values 1 to k, where the classifier actions take values from 1 to k plus 1. And we will interpret the action k plus 1 of the classifier as the classifier rejecting the pattern. It is rejecting the pattern because maybe it does not have enough confidence to classify. So, now for this case, let us put some loss function. So, as you know, the loss function has two arguments. The first argument is what I call I here, is the actions of the classifier. Second argument are the class labels. So, I can take values 1 to k plus 1, whereas j takes values only 1 to k. So, this is something like a 0-1 loss function. So, if I did correct, so if both I and j belong 1 to k, that means the classifier has classified the pattern to one of the classes, and if I is equal to j, then loss is 0. Similarly, if I is 1 to k, that is the classifier has decided to call a particular class, but I is not equal to j, then we misclassified. Let us call that cost rho m for misclassification. On the other hand, in respect of j, if I is k plus 1, that is the classifier has decided to reject the pattern, the loss is rho r. Okay. So, this is the loss function. So, if I misclassify a pattern, I suffer a loss of rho m. If I reject a pattern, I suffer a loss of rho r. Of course, correct classification is 0 loss. Given this, can we now derive the base classifier in terms of the posterior probabilities as usual? Okay. Recall that the general base classifier is given an x, the base classifier will say alpha I or I. If the risk of that action is less than the risk of all other actions, where risk of that action given x is defined as L of alpha is Cj Qj x, where j or Cj are the class label. So, j goes from not 0 to 1, I am sorry, 1 to k, not 0 to k, but 1 to k. I am sorry about that. So, that k classes. So, now we will calculate this risk for various actions and say when is classification better and when is reject better. When the classifier wants to take actions 1 to k, that means classify into one of the classes, then the loss is rho m if I misclassify, otherwise it is 0. So, for I between 1 to k, the risk of I given x is rho m q j, j not equal to I, because when I correctly classify, there is no loss. Otherwise, all other misclassifications are the same loss rho m. So, now rho m comes for the summation and it becomes rho m into 1 minus q I x. On the other hand, if classifier takes the action k plus 1, then for all class labels j, the loss is rho r. So, the risk will be summation over j rho r q j, rho r comes for the summation and sum over j q j is equal to 1. So, this becomes rho r. Here, because the summation over j not equal to I, summation q j will become 1 minus q I. Here is for all j. So, summation q j becomes 1. So, this becomes rho r. So, what does it mean? When can I call a particular class I R I given x should be better than R j given x for all other class labels j, and it also should be better than R k plus 1 given x, right. So, my base classifier can say I for one of the class labels if the risk associated with I, that is rho m into 1 minus q I, should be less than or equal to risk associated with any other class label rho m into 1 minus q j. Also, risk associated with action I should be less than the risk associated with the action k plus 1, which is rho r. So, both these have to be satisfied for me to call class I. So, let us simplify this. So, the base classifier will now say a class label I if rho m into 1 minus q I x is less than rho m into 1 minus q j x for all j, as well as rho m into 1 minus q I x is less than rho r. The first inequality, I can cancel rho m from both sides, and first inequality becomes same as q I greater than q j. So, let us simplify the second also. So, I can call I, the first inequality says q I greater than or equal to q j, and the second inequality says I will bring rho m this side, is 1 minus q I less than rho r by rho m, or if you bring q I the other way, q I is greater than 1 minus rho r by rho m. So, if both these conditions are satisfied, then I can call a class I. Obviously, there will be some I for which q I is greater than or equal to q j, whichever is the highest posterior probability class. But earlier, when I did not have reject, the base classifier simply puts it in the class corresponding to the highest posterior probability. But now, that is not enough. For me to call a class, because I am allowed reject, not only I should be the highest posterior probability class, but the probability of the highest posterior probability class itself should be greater than some threshold. If this is not true, then it is better to call reject. Otherwise, HBX will be k plus 1, because this inequality is not satisfied, which means the least risk will be for the action k plus 1. So, let us try and understand it again. So, in the reject case, my new base classifier will say a class label I if this is true, that the highest posterior probability is greater than 1 minus rho r by rho m, and then I will call the highest posterior probability class. Otherwise, I will call k plus 1. To understand this, let us look at few special cases. Suppose cost of rejection is greater than cost of misclassification. What does that mean? If I misclassify a pattern, I suffer less loss than if I reject a pattern. Then that doesn't, then it should not be, there should be no condition under which reject is good. Now, that is what this will tell me. If rho r is greater than rho m, then rho r by rho m will be greater than 1. So, 1 minus rho r by rho m will be negative, and hence q I being a probability will always be greater than this. So, then it boils down to whole thing. For some I say that q I x is greater than q j, I will call that I. I will never ever call k plus 1, right. So, I never reject a pattern. Now, consider the other extreme case. Suppose cost of rejection is 0. Cost of rejection is same as cost of correct classification. So, what should I do? Might as well reject everything. What does my derivation say? If rho r is 0, I will call one of the class labels only if q I x is greater than or equal to 1. So, what does that mean? If cost of rejection is 0, I always reject a pattern, unless of course, I am absolutely sure. If q I x is equal to 1, then I can call I. Unless I am absolutely sure, it is better to reject a pattern, because rejection costs me nothing. So, these are just extreme cases for us to understand that this is nice. So, this is another example of how I may derive a base classifier, where classifier actions may be different from class labels. Here we have one extra action, namely the reject option. Okay. So, with this example, we will stop discussing examples of base classifier. Let us move to one other important issue with base classifier. How do I find the base error? From all the examples we considered so far, given class conditional densities, the base classifier is easily computed. Right. For various loss functions, we know how to compute it. Now, we may also want to compute the base error, because that tells me what is the expected error of the classifier, what is the expected risk of the classifier. Now, for example, if the expected risk is not within acceptable limits, expected error rate is not within acceptable limits, then I may have to rethink my whole problem. In the sense, I may want to get better features, because with these features, this is the best performance I can get. So, estimating or finding base error is useful for me to know whether my classifier will meet the specification requirements. Okay. So, for the 0 1 loss function, we already seen when we derived the optimality base classifier that this is the error. So, we have to integrate minimum of P0, F0, P1, F1 over the entire feature space to find the error rate of the classifier. This is the probability of misclassification by the base classifier. In general, this is a very difficult integral to evaluate because there is a mean inside the integrand. First, let us look at a very simple case. Let us consider one dimensional feature space, two class problem, 0, 1 loss function. Assume equal priors, okay. Assume normal class conditional densities with equal variance. This is about the simplest special case you can consider. And for notational convenience, let us assume the mean of class 0 is less than mean of class 1. In this case, we already know because the both variances are same, the threshold for the base classifier is midway between the two means. So, if x is less than mu 0 plus mu 1 by 2, I will call class 0. If it is greater than that, I will call class 1. Okay. This is the base classifier. So, what will be the error of the base classifier? So, for x less than mu 0 plus mu 1 by 2, I will always call 0. So, the probability of class 1 patterns coming with x less than this is 1/2 of the error. So, probability that x belongs to class 1 and x is less than mu 0 plus mu 1 by 2 is this probability, this integral of the f1, the class 1 class conditional density over this range. Similarly, the other error occurs when a class 0 pattern comes with x greater than mu 0 plus mu 1 by 2. Okay. So, this is the base error. For normal densities, this is easy to evaluate. So, let us evaluate it. So, this is the error integral. F1 is normal with mean mu 1 and variance sigma. F0 is normal with mean mu 0 and variance sigma. So, using the standard substitution, if I change the variable x in this integral to z, where z is x minus mu 1 by sigma, then this density assume the form of the standard normal density. Similarly, for this integral, because F0 is normal with mean mu 0 and variance sigma, if I use the substitution z is equal to x minus mu 0 by sigma, this becomes a standard normal density integral. Now, what happens to the limits? When I put z this, when x goes up to mu 0 plus mu 1 by 2, z goes to mu 0 minus mu 1 by sigma, and similarly here. So, this becomes an integral of the standard normal density over minus infinity to mu 0 plus mu 1, mu 0 minus mu 1 by sigma, and this becomes from mu 1 minus mu 0 by sigma to infinity of another standard normal. So, the error density is this, where phi is the distribution of the standard normal density. So, the first integral is from minus infinity to mu 0 minus mu 1 by sigma. So, that is phi of mu 0 minus mu 1 by sigma. Second integral is from mu 1 minus mu 0 by sigma to infinity. So, this is 1 minus phi of mu 1 minus mu 0 by sigma. Okay. Because the distribution function of standard normal is symmetric, phi of 1 minus phi x is equal to phi of minus x, right. What is in this big brackets here is same as this. So, the 0.5 goes away. So, the error becomes this. Okay. So, for equal variance, both class conditional densities being normal, this is the base error. Okay. So, essentially base error depends on mu 0 minus mu 1 by sigma. As you would expect, when sigma is same, I am just putting the point midway. So, how much error I make depends on how much the means are separated. If means are separated by a large amount, then I will make less error. If means are separated by a small amount, I will make more error. And small and large amount is relative to the variance of the distribution, right. So, that is what this expression denotes. The quantity mu 0 minus mu 1 by sigma, where mu 0 minus the absolute value of mu 0 minus mu 1 by sigma is called the discriminability. This when this quantity is large, right. Note that we are assuming mu 0 less than mu 1. So, when discriminability is large, this will be phi of some large negative quantity, so close to 0. So, if mu 0 and mu 1 are separated by a large amount relative to the variance, then I make very small error. If they are separated by a small amount, then I will make a large error, the base error. So, that is why this quantity is called the discriminability. Now, this is for a very special one dimensional case, normal densities with equal variance. What about the general case? In general, we have to evaluate this integral. As I already said, mean inside the integrand is often difficult to evaluate, but one can use one very standard and useful inequality for any two real numbers a and b. Mean of a comma b can always be bounded above by a to the power beta into b to the power 1 minus beta, for any beta between 0 and 1. Here we are assuming that both A and B are positive numbers. Okay. This bound is not difficult to prove, so let us prove this. Let us suppose A is less than B. Now, what is A power beta into B power 1 minus beta? I can write it as A power minus 1 plus beta, that is divide by A and then multiply by A. Now, this becomes B by A whole to the power 1 minus beta into A. Now, I am assuming B greater than A, so B by A is greater than 1. So, B by A to the power 1 minus beta is some quantity greater than 1. So, when you multiply that with A, I get some quantity greater than 1 and A is of course mean of A comma B. So, this shows that mean of A comma B is bounded above by A power beta into B power 1 minus beta. Okay. So, I can reduce this integral to, I can write this mean, bound this mean by this to the power beta and this to the power 1 minus beta, that becomes P0 to the power beta, P1 to the power 1 minus beta, integral of F0 to the power beta and F1 to the power 1 minus beta. This is slightly easier integral to evaluate than this, because I do not have mean inside. It is the normal density raised to some fractional power. Even then, it is a difficult integral to evaluate. But suppose if I assume that F0 and F1 are some multidimensional Gaussian densities, F0 has mean mu 0 and covariance matrix sigma 0, F1 has mean mu 1 and covariance matrix sigma 1, then one can show that this integral can be bounded above by e power minus k beta, where that k beta is some involved expression like this, essentially some kind of a quadratic form involving mu's and sigma zeros. But anyway, this can be shown, it is just a algebraically difficult, but otherwise this derivation is straightforward. So, one can show this. Okay. So, what does this mean? That P error is less than or equal to P0 power beta, P1 to 1 minus beta exponential minus k beta, where the k beta term is given by this, which I can calculate if I know mu 1, mu 0, sigma 1. Okay. Now, how can I use this bound? This bound is true for all beta between 0 and 1. So, for example, I can ask which beta will give me the tightest bound. So, we can choose a beta and calculate a bound from this expression. A bound calculated like that is often called Chernoff bound. We can get a tighter bound by choosing beta that minimizes this expression. Such a bound is called a Chernoff bound. If we do not want to do all that work, in practice a beta that often works is beta is equal to 0.5, and the bound on the base error obtained through this expression, where they choose beta to be 0.5, is known as the Bhattacharya bound. Okay. There is another bound on the base error. Okay. Because in general this bound can always be used, though for general class canonical densities I will not have this exponential minus k beta, I will have that actual integral, and we need to know how to evaluate it. But even for normal class canonical densities, as you can see, we can only bound the base error. It is not easy to actually compute the base error. Okay. But this is one way in which I can estimate the base error, either using Chernoff bounds or the Bhattacharya bound. Okay. All right. Let us move on from base classifier. Base classifier is optimal for the criterion of risk minimization, but risk minimization is only one criteria, right? We can have many other criteria. What does risk minimization? There is one thing about base classifier, it depends both on the prior probabilities and class conditional densities. Now, very often I may not know prior probabilities out there in the field, which patterns will come I may not know, though I may be able to estimate the class conditional densities well. So, sometimes we may want a classifier that does well against the worst kind of prior probabilities. Okay. So, without knowing what the prior probabilities is, I do not want my base classifier to depend on priors, because one day I might have to work with predominantly one class patterns, another day I might have to work with predominantly another class patterns. So, I can ask, minimizing risk is not what I want a classifier that has the best risk against the worst possible prior probabilities. Okay. Now, this of course will not be the base classifier, because I do not know the priors. Let us just intuitively see what this will mean. Let us say we will take a two class case, as earlier, let us say RIH denotes the subset of feature space, where the classifier H will put things in class I, that is R0 is the region of class 0, R1 is the region of class 1, and by region I mean not the actual region of the class 1 or class 0 feature vectors, but that subset of the feature space where the classifier H will put the patterns in that particular class. Then if from what we derived earlier, the risk integral is the probability that a class 0 pattern comes into a region where H will put in class 1, and the probability that a class 1 pattern will come into a region that H will put in class 0. This is the same integral that we got earlier. Now, what we want to do is, we want to manipulate this expression so that it becomes independent of the prior probabilities. We can do that because we know that P0 is 1 minus P1 or P1 is 1 minus P0. So, we can eliminate one of them. So, this is my risk integral. Over R1, it is L10 P0 F0, over R0, it is L01 P1 F1. Now, I can eliminate one of P0 and P1. Let us say I will substitute P1 is equal to 1 minus P0. So, that is my risk integral. Now, this integral has one term which is constant, L01 into integral of F1 over R0, and another term that depends on P0, P0 into this first integral minus the second integral. Okay. So, I can write the risk as one constant term plus P0 times difference of two integrals. Now, for a classifier which chooses the regions R0 and R1 in such a way that this expression in these big brackets goes to 0, that classifier's risk is independent of priors, right. The way the risk is written, if there is a classifier which chooses class 1 and class 0 decision regions R1 and R0 in such a way that this expression becomes 0, right. The second term in this expression becomes 0. For that classifier, the risk will be independent of the priors, right. So, consider a classifier which chooses any classifier. What do you mean design of a classifier? Once I design a classifier, I have designed a function from the feature space to the set 0 1, because we are considering a 2 class problem. So, which means each classifier simply assigns some subset of the feature space where it will, if a feature vector falls in that subset, I will call class 0. Similarly, the remaining subset I will call it class 1. So, a design of every classifier is simply choosing a region R1 where I will call class 1 and choosing a region R0 where I will call class 0. So, a classifier designed in such a way that the regions R0 and R1 are so chosen, so that this equation is satisfied. Where did I get this equation from? This is nothing but the term here, right. I wanted to make this term 0. So, that term will become 0 if this equation is satisfied. For such a classifier, the risk could be independent of priors. So, this classifier is known as min-max classifier, because it can be shown, it is easy enough to see that we are minimizing the maximum possible risk over all possible priors, because we are cancelling out the prior dependence and risk. So, we are budgeting for the maximum possible risk, where maximum is over all possible priors for the same class-Kanischl densities. Of course, finding analytically a classifier that satisfies this expression is not easy. In general, finding min-max classifiers is an analytically complicated issue, but the purpose of mentioning min-max classifier here is just to say that risk minimization is not necessarily the only criterion we can have when we are looking for classifier. Here is another example of a classifier which is different from Bayes, but it has its own optimality criterion, the min-max classifier, which minimizes the maximum possible risk, where maximum is or all possible priors. Let us look at one more criterion. This is also a very famous criterion called Neyman-Pearson criterion. To understand this criterion, let us go back to Bayes classifier again. Bayes classifier minimizes risk. What is risk? Risk is expectation of loss. So, each loss is what I pay for an error, and because in expectation, it is some weighted sum of the errors, right, weighted sum of probability of errors, weighted sum of losses. So, if I classify a class 0 pattern as class 1 pattern, there is some cost associated with it. Class 1 pattern as class 0 pattern, there is some other cost associated with it. I find weighted sum of all such costs and asking which classifier minimizes it, and that happens to be the Bayes classifier. But the two kinds of errors may not always be tradable. This assumes that if cost of one kind of error is 3 times cost of another kind of error, we are saying is better to make 2 errors of one kind than 1 error of this kind, right. That is the trade off we are doing in minimizing risk. But there would be situations where we may not want to trade one type of error with another type of error. Okay. So, for example, instead of trading errors, we can say for a fixed constraint on type 1 error, minimize type 2 error. Recall that type 1 error is wrongly classifying a class 0 pattern. Why would this may be possible? Let us suppose you are in a biometric application. Suppose you are authenticating identity of somebody. So, there are 2 kinds of errors. When somebody is an imposter, allowing him access is one kind of error. A authorized person not being allowed access is another kind of error. Now, the 2 kinds of errors are qualitatively different, and I don't want to find optimal by saying so many times this error plus so many times that error should be minimized. On the other hand, I may say that I don't want more than 1%, more than 0.1% of the time an unauthorized person gaining access. While maintaining that, can you give me the best possible error rate for the other kind? Right. So, I will put a particular threshold for type 1 error. That is, I do not want more than 1 in 1000, more than once in 1000 times an unauthorized person should gain access. And among all classifiers that meet this specification, I want a classifier which minimizes the error of throwing away an authorized person, because throwing away an authorized person is only an irritation. Right. So, there are applications where you do not want to trade errors of one kind with the other. I may want to put a threshold on the error of one kind. That is, I want error of one kind should not exceed a probability of error of one kind should not exceed something, and given that I want to then minimize the other kind of error. So, it's as I said, it is generally useful in biometric applications where, as I said, I may want to put an absolute bound on how often I may allow an unauthorized person to gain access, and while I am satisfying the specification, I want to minimize the number of times I will throw away an authorized person. So, type 1 error is, let us say, wrongly classifying class 0 pattern, and let us say upper bound and probability of type 1 error is alpha. So, the Neyman Pearson classifier is a classifier that achieves a bound of alpha on type 1 error, that the probability of type 1 error by Neyman Pearson classifier is less than or equal to alpha, and in addition it minimizes the other kind of error. As a matter of fact, Neyman Pearson classifier can also be expressed as threshold on likelihood ratio. As we seen in base case, it is simply a ratio on the posterior probabilities or class canonical densities. We put a threshold on this ratio. Neyman Pearson classifier can also be expressed, and we will see how. So, let us first define the Neyman Pearson classifier. The Neyman Pearson classifier, let us call it HNP. Earlier we were calling base classifier as HB. So, we will call it Neyman Pearson classifier HNP. So, given any alpha in 0, 1, this is the upper bound on the type 1 error. What does HNP have to satisfy? Firstly, probability HNPX is 1 given x belongs to C0, that is wrongly classifying a class 0 pattern is bounded above by alpha. Right? This is one thing that HNP has to satisfy. Then what does it have to satisfy? Wrongly classifying a class 1 pattern, that is the other kind of error, probability HNP 0 given x belongs to C1, that should be less than the probability of wrongly classifying a class 1 pattern by any other classifier H. But this is not for all H, but only those H which also meet the bound on the type 1 error, because NP minimizes the second kind of error while satisfying the bound on the first kind of error. So, among all classifiers H that satisfy the bound on type 1 error, so if H is such that probability Hx equal to 1 given x belongs to C0 is less than or equal to alpha, that means this classifier H also satisfies the type 1 error bound, then the probability of the type 2 error by H and P is less than or equal to probability of type 2 error by H, right. I hope it is clear. So, the Neyman Pearson classifier is characterized by, firstly, its type 1 error is bounded by alpha, and its type 2 error, that is wrongly classifying class 1 pattern, is less than the type 2 error of any other classifier H if H also satisfies the bound on the type 1 error. Okay. Now, this is what the Neyman-Pearson classifier is. Let us suppose the bond is alpha as we are saying. Then the HNP classifier is the Neyman-Pearson classifier is defined by, it will assign class 1 to X if F1x by F0x is greater than K, otherwise assign class 0, where F1 is the class conditional density for 1 and F0 is class conditional density for class 0, where the K itself is obtained by under the distribution of class 0, that is under the distribution of F0, the probability that this ratio is less than or equal to K is bound above by is equal to 1 minus alpha. Okay. So, I choose a K. See, this is some probability involving the random variable X under the distribution F0. You think of this F1 and F0 simply as some functions. So, F1 by F0 is some other function g of x. So, this is probability g of x less than or equal to K under the condition that x is distributed as F0. X belongs to 0 means x is distributed as F0. Right. What does this ensure? This ensures that my type 0 error is equal to alpha. When will I wrongly classify a 0 pattern? I will call class 1 if this ratio is greater than K. When x belongs to C0, this ratio will be greater than K. The probability the ratio is greater than K is equal to alpha, because K is chosen to satisfy this equation. The ratio is less than or equal to K is 1 minus alpha. So, the probability ratio is greater than K is equal to alpha. Right. So, by construction, the Neyman-Pearson classifier satisfies the bound on type 1 error. Okay. We'll see it once more. Just for completeness sake, the way we stated this, we are assuming that F1 and F0 are true density functions. That is, probability x belonging to any lower dimensional subspace. For example, a subspace that is characterized by F1x equal to K F0x. This is 0. Okay. So, because we are assuming that the ratio is either greater than K or less than or equal to K. Okay. So, we will not allow any kind of Dirac delta part in the F1 F0. This is only a technical condition. Those of you who do not understand this, don't worry about it. Simply assume that F1 and F0 are nice smooth density functions, then this will be all right. Okay. So, now let us prove that the classifier that we put here, right. This is the specification. This is how Neyman-Pearson classifier will classify a new pattern X. This classifier is actually the Neyman-Pearson classifier. That is, it satisfies the two conditions that we set down for the Neyman-Pearson classifier. What are the two conditions? First is type 1 error should be less than or equal to alpha. For the type 1 error, h and p x equal to 1 given x belongs to C0. When will h and p x be 1? By definition, h and p x is 1 if f1 by f0 is greater than k. So, probability h and p x equal to 1 is probability f1 by f1x by f0x is greater than k, and when x belongs to C0. This where the k in the Neyman-Pearson classifier is obtained by this equation. So, this equation ensures that probability f1 by f0 greater than k is equal to alpha. Right. So, the probability of type 1 error by Neyman-Pearson classifier is alpha. So, it satisfies the first criteria. So, now we have to show that this type 2 error is less than that for any other classifier, which also satisfies the constraint on the type 1 error. Okay. So, let us prove this. So, let H be any other classifier which also satisfies the constraint on the type 1 error. That is, probability Hx equal to 1 when x belongs to C0 is less than or equal to alpha. Then, to complete the proof, we have to show that the type 2 error of H and P, that is, probability H and P x equal to 0 when x belongs to C1 is less than or equal to probability Hx equal to 0 for when x belongs to C1. Okay. So, this is what we will next show. We actually will not show it in this form. The way we will show it is, we will show the complement of this event. So, we will show that the probability h and p x is equal to 1 when x belongs to C1 is greater than equal to probability h x equal to 1 when x belongs to C1. So, instead of showing probability h and p x equal to 0 is less than probability h x equal to 0 when x belongs to C1, instead of showing this is less than this, we are showing that the complement event HNPX equal to 1 is greater than probability Hx equal to 1. Okay. To show this, let us consider the integral I, which is the integral over the entire feature space of the product of two terms. The first term is HNPX minus Hx, second term is F1x minus Kf0x, where K is the threshold used in the NP classifier. Recall that HNP and H in this case are binary valued functions. HNP takes value 0 or 1, Hx also takes value 0 or 1. So, HNP minus Hx is some real number. As a matter of fact, it can be only either minus 1, 0 or plus 1. Okay. What we are going to show first is that this integral will always be positive, and then we show that that completes the proof of the the classifier that we gave is the Neyman-Pearson classifier. Let us first note that I can split this integral into two parts. Integral over all x such that f1x is greater than kf0x, and integral over all x such that f1x is less than or equal to kf0x. This splits Rn into two parts, and we are going to show that for each half the integral is positive. Okay. Positive means greater than or equal to 0, that is non-negative. So, first let us consider all x such that f1x is greater than kf0x. Recall that HNPX says HNPX equal to 1 if f1 by f0 is greater than k. So, for all x such that f1x is greater than kf0x, we have HNPX is 1, which means HNPX minus Hx will be 1 minus Hx, which is always greater than or equal to 0, because Hx can be either 1 or 0, right. No matter what classifier H is, Hx is either 1 or 0. So, for all x such that f1x minus kf0x, f1x is greater than kf0x, HNPX minus Hx will always be greater than or equal to 0, which means HNP minus H into f1 minus kf0 is positive, because both terms here are positive. Now, let us look at the other way around. Let us look at all x such that f1x is less than kf0x. Now, HNPX will say 0, right. Those x's are put in class 0 by Neyman-Pearson classifier. So, HNPX is 0. So, HNPX minus Hx will be 0 minus Hx, which for any classifier Hx is less than or equal to 0, because Hx can be either 0 or 1. So, once again the product HNP minus H into f1 minus kf0 is positive, because both factors here are negative, okay, which means the integral we started with is always positive. Okay. So, what we have shown so far is that this integral is positive. Okay. So, now let us expand this integral by multiplying these two terms. So, multiply with f1 first. So, I get HNP into f1 minus H into f1, okay. Those are the first two integrals. Take the other terms on the other side. So, this is greater than or equal to k times HNP into f0 minus H into f0, because I have taken them the other side. Now, HNP term will become positive, right. I just multiplied this term and put two integrals on this side and two integrals on this side. Okay. Since HNP and H are binary valued functions, for any given x, HNPX is either 0 or 1. Similarly, H is either 0 or 1. So, if I take an integral over entire feature space Rn, HNP into f1x dx, it is simply integral of f1 over the region over the set of all x such that HNPX is 1, right. Because I am integrating over f1, this integral is nothing, integrating with f1 here, the integral is nothing but condition on x belongs to C1, probability that HNP is 1, right. Because HNP is a 0, 1 valued function, integral HNP into f1 over Rn is same as integral f1 over x such that HNPX is 1, which is same as, because I am integrating f1, which is same as probability HNPX equal to 1, condition on x belongs to C1. Similarly, for H, because H is also 0, 1 function, integral H into f1 is probability that Hx is 1, condition x belongs to C1. Similarly, the integral with respect to f0. Okay. So, which means each of these integrals, this can be written as probability HNPX equal to 1, condition on x belongs to C1. This is Hx is equal to 1, condition on x belongs to C1. Similarly, this is HNPX is 1, conditioned on x belongs to 0. Hx is 1, conditioned on x belongs to 0, right. So, this inequality can now be written as probability h n p x equal to 1 given x belongs to C1 minus probability h x equal to 1 given x belongs to C1 is greater than or equal to k times probability h n p x equal to 1 condition x belongs to C0, probability h x equal to 1 condition x belongs to C0. Let us also remember that this factor k will always be positive, right, because two ways of looking at it. K is defined by the definition of Neyman-Pearson classifier. This is the definition of Neyman-Pearson classifier, because both f1 and f0 are density functions, they are always positive. So, this ratio is always positive. So, if k is negative, is forever satisfied. So, that is one way of looking at it. Any case, because this is some positive function of x and we want it less than or equal to k, has to have some positive probability, k has to be a positive number, right. Given that k is a positive number, let us look at what is there in the brackets here. This is h n p x equal to 1 condition x belongs to C0 minus h x equal to 1 condition x belongs to C0. Now, this is the type 1 error of h n p x of the Neyman-Pearson classifier, which by construction is alpha. This is the type 1 error of the classifier h, and because h is something that satisfies the constraints on type 1 error, this is less than or equal to alpha. So, this factor is greater than or equal to 0, right. So, for all h under consideration, all h that satisfy the constraints on type 1 error, right, the term on the RHS is always non-negative, which means this is positive. H n p x equal to 1 condition x belongs to C1 minus h x equal to 1 condition x belongs to C1 is greater than or equal to 0. This shows that the Neyman-Pearson classifier has the smallest type 2 error compared to smaller type 2 error compared to any classifier that also satisfies the type 1 error bound, right. This shows that the classifier that we have actually put down as Neyman-Pearson classifier satisfies the criteria for Neyman-Pearson classifier. So, Neyman-Pearson classifier also needs the knowledge of class conditional densities, because you have to calculate f0 by f1. Like Bayes classifier, it is also based on the ratio f1 by f0. In Bayes classifier, we say C1 if f1 by f0 is greater than some threshold, which happens to be P0 L0 1 by P1 L1 0. In NP, this is some other threshold k, which is set based on the allowed type 1 error. Okay. So, both of them essentially threshold the ratio of the two class conditional densities. So, let us quickly look at a simple example of Neyman-Pearson classifier. Let us take a one dimensional feature space, normal class conditional densities with equal variance. I suppose by now, if you have been following all the lectures, you know that this is always the simplest case. A two class problem, one dimensional feature space, normal class conditional densities, equal variance. Okay. For concreteness, let us assume that mu 0 is less than mu 1. Mu 0 is the mean of the class 0 and mu 1 is mean of class 1. So, what is the NP classifier? If x greater than tau, then C1. Where how do I choose tau? Tau is simply determined by the type 1 error bound. Okay. So, let us derive this formally. How do I get this tau? Okay. Because both f1 and f0 are normal, it is easy to see f1 by f0 exponential minus x minus mu 1 whole square by 2 sigma square plus x minus mu 0 square by 2 sigma square. The other factors 1 by sigma root 2 pi will cancel, right. Now, we can expand this, the x square term will cancel. So, what will I get? Minus 1 by 2 sigma square, mu 1 square from here, mu 1 square from here, minus mu 0 square from here, right, and 2x into mu 1 minus mu 0. I can absorb this minus sign. So, I can write it as mu 1 minus mu 0 by 2 sigma square into 2x minus mu 1 plus mu 0. This is the ratio of f1 by f0 for the case of normal densities with equal variance. Okay. We need to find a k such that probability f1 by f0 less than or equal to k is 1 minus alpha, because log is a monotone function which is same as probability log of f1 by f0 less than or equal to log of k condition on C0, that is also good enough. Okay. Now, this is f1 by f0. So, log of f1 by f0 will be just simply what is inside the exponent. So, what we get is mu 1 minus mu 0 by 2 sigma square into 2x minus mu 1 plus mu 0 should be less than or equal to log k. So, I can use this. So, this is some expression involving the random variable x, right. I want the probability of this event to be equal to 1 minus alpha. How to choose k like that? Okay. So, we can do it like this. So, what will this give me? I can first take 2 sigma square by mu 1 minus mu 0 this side, right. Then bring mu 1 plus mu 0 on this side, and then I will get 2x here, divide by 2. So, this inequality is same as x less than or equal to sigma square ln k by mu 1 minus mu 0 plus mu 1 plus mu 0 by 2. So, what we want is, let us say p subscript 0 is the probability condition on x belong to class 0. So, p0 ln f1 x by ln of f1 by f0 less than or equal to ln k is same as p0 of x less than or equal to that quantity. Now, because this is a p0 probability means I am taking the probability under the class 0 class conditional density, that is mu 0 mean and sigma variance. So, I can write this as this x less than this same as x minus mu 0 by sigma less than something else. So, just subtract mu 0 and divide by sigma, I get this expression. Okay. Why did I do that? Because I know the distribution of x minus mu 0 by sigma, because x is under this probability x belongs to C0, C0 is normal with mean mu 0 variance sigma, x minus mu 0 by sigma is standard normal. So, this probability is given in terms of the standard normal function phi of this quantity sigma ln k by mu 1 minus mu 0 plus mu 1 minus mu 0 by 2 sigma, where phi is the density of the standard normal. Okay. So, ultimately to get k, I have to equate this quantity to 1 minus alpha. Alpha is given in Neyman-Pearson criteria, what I am given is alpha, that is the allowed type 1 error bound. So, to get k, I have to equate this to 1 minus alpha. So, let us equate that, phi of this equal to 1 minus alpha. So, now I can solve this for k or ln k, that gives me sigma ln k by mu 1 minus mu 0 is phi inverse of 1 minus alpha minus mu 1 minus mu 0 by 2 sigma. Now, multiply by mu 1 minus mu 0 divide by sigma, that gives me ln k is this much. Okay. From this I can get k. Okay. So, this is the threshold I want for Neyman-Pearson classifier. Let us ask what does the classifier mean. So, in Neyman-Pearson classifier we will put x in class 1 if f1 by f0 is greater than k, which is same as ln f1 by f0 greater than ln k, and the ln k is given by this expression that we have just now derived. So, I will put x in C1 if ln f1 by f0, that is this expression, is greater than ln k, that is this expression. Okay. Now, I can simplify this expression. 2x minus mu 1 plus mu 0 is multiplied by 2 sigma square and divided by mu 1 minus mu 0, I get this, right. 2 sigma phi inverse 1 minus alpha minus mu 1 minus mu 0. Remember, we are assuming mu 0 less than mu 1. So, mu 1 minus mu 0 is a positive quantity. So, when I divide by it, the inequality does not change. Now, we bring mu 1 minus plus mu 0 on this side and divide by 2, this is same as x greater than this, which. So, the Neyman-Pearson classifier will put x in class 1 if x is greater than this, which is same as x minus mu 0 by sigma and bring phi inverse this side, phi of x minus mu 0 by sigma is greater than 1 minus alpha, right. What is phi of x minus mu 0 by sigma? That is the distribution of the standard normal density. So, what does this mean? This means this threshold x greater than tau, if I think of this as tau, the integral of the density function of class 0 starting from this tau to infinity will exactly be equal to alpha, right, because phi of this is greater than alpha, what is remaining in the integral will be equal to alpha. So, let us look at this, what it means. So, if this is my f0, I am choosing a tau as my threshold such that this area from tau to infinity is equal to alpha. That is the allowed type 1 error. Okay. So, the Neyman-Pearson classifier ultimately that ratio being some greater than k turns out to be same as x greater than tau, where tau is chosen so that tau to infinity f0 x dx equal alpha. This is what we want, because in when they are normal and equal variance, ultimately the classifier is a threshold, and type 1 error, because we are assuming mu0 is less than mu1, type 1 error is simply integral from tau to infinity of the class 0 density function. Okay. So, like the Bayes classifier, the Neyman-Pearson classifier also needs knowledge of class conditional densities, and the classifier is only for 2 class case. We did not define for multi-class case, and is often difficult to define for extend to multi-class case. Just as general information, it is more important in certain statistics problems called hypothesis testing problems, okay, more than classifier. Though for 2 class case, it is also used, especially when you do not want to trade one kind of error with another. Rather than that, you want to put a bound on one kind of error, and given that bound is satisfied, minimize the other kind of error. Okay. Actually, as we see in the Neyman-Pearson classifier, is for trading one kind of error with another kind of error. Okay. So, this kind of thing happens in many other ways. A good way of looking at it is what is called the receiver operating characteristic. If you consider a one dimensional feature space 2 class problem with Hx equal with a particular threshold tau. Now, if I think of class conditional densities once again as normal with equal variance 0 1 loss function, we can write the error as a function of tau. Below tau I am putting class 1, above tau I am putting class 2. So, this is my error integral, as we have already written earlier, right. So, my error integral is because priors are equal 0.5 times probability that class 1 pattern comes below tau, and 0.5 times probability that class 0 pattern comes above tau, right. Once again, I can, because f1 and f0 are normal, I can write the standard normal. As we vary tau, essentially we are trading one kind of error with another. When I change tau, one kind of error may increase and other kind of error will decrease. So, varying tau allows us to trade one error with another, and hence at least in a threshold based classifier, we can actually sit and decide how we want to do the trade off, right. Risk function is one way of doing the trade off, where the loss function gives me, so to say, the exchange rate. How much of one kind of error I can trade for how much of other kind of error, that the relative values of the 2 losses. Neyman-Pearson criteria gives me another way of trading these errors, right. I want this error below some alpha and minimize the other error, but I can choose my own trade off, right, by using what is called a receiver operating characteristic. The receiver operating characteristic curve is one way of conveniently visualizing this trade off. For a 2 class classifier, there are 4 possible errors, right. 2 are correct, 4 possible outcomes of a classification decision, 2 are correct and the other 2 are wrong. Let EI denote the probability of wrongly assigning class I, that is E0 is wrongly assigning class 0 and calling 0 when it is actually 1. Let us say E1 is wrongly assigning class 1, which means calling 1 when it is actually class 0. Okay. So, actually I can define this like this: E0 is the probability that when x is actually in class 1, x is also less than tau, so I call class 0, is called a miss. Okay. E1 is wrongly assigning class 1, that is, even though x is actually comes from C0, because x is greater than tau, I call class 1. This is called a false alarm, right. The 1 minus E0 and 1 minus E1 probabilities are called the correct detection and correct rejection. For fixed class conditional densities, if we vary tau, the point E1 comma 1 minus E0 moves on a smooth curve in R2. Okay. Of course, I could have chosen any two of these numbers. The choice of coordinates is arbitrary, but this curve which plots the false alarm rate versus the correct detection rate, that is E1 versus 1 minus E0, right, for various values of tau, right. That is on the E1 1 minus E0 plane. For each tau, there is one value of E1, one value of 1 minus E0. So, as I vary tau, it becomes a smooth curve, and such a curve is called the receiver operating characteristic. Okay. This is another way of trading one kind of error with the other kind of error. Okay. So, let us close down today's class with a summary. The Bayes classifier is optimal for minimizing risk. We have seen that last class, and we have seen a couple of more examples this class. We can derive Bayes classifier if we know the class conditional densities, and for various kinds of loss functions we can derive. There are criteria other than minimizing risk. As we have seen, minimizing risk is not the only way we can run this problem. For example, min-max classifier, Neyman Pearson classifier are some examples of criteria other than minimizing risk. All of these are essentially trying to trade off errors in a way different from the trade off that the Bayes classifier does. Bayes classifier trades off errors using the loss function of the exchange rate, whereas there are other ways of trading of errors, and receiver operating characteristic curves allow us to visualize the trade off between different types of errors as we vary the threshold. We will once again briefly look at the receiver operating characteristics next class. Thank you.